We're live. Hello, everyone. Welcome to today's new Corecast episode. I'm your host, Tim.
And I'm Mikey.
Oh, it's a little strange.
So
I guess he was.
Sahil's not here, so I'll be playing the part of Sahil today. So Tim, in high school, I learned uh, that there are three phases of matter. You know, what is it like? Liquid, solid, and gas. And so my question is, are there really just three phases of matter? And why can't there be more?
Yeah, and I think that's something every physics student kind of goes through, right? Like in the beginning, we always tell people we always learn like the simplified version of stuff that there are three phases of matter, but quickly as we went through higher education, we realized that three phases is just kind of happenstance. It just happens that these are the ones that we're most familiar with on Earth, like liquid, solid, and gas. And turns out that there are actually a bazillion different phases of matter, depending on the material, depending on circumstances. So indeed, three is not really any particular magic number. So there actually are more phases of matter. So
Yeah.
I guess I mean I guess one interesting question as we learn through these physics scenario is also that phases don't actually they don't just apply to matter. They also apply to forces.
Wait, so yeah, what is a phase? Let's back up first of all. What do you say? What do you mean by that?
I think phase is I think it is somewhat of a vague definition. A phase of matter generally is a sort of I think we would quantify phase as a distinctive uh, as for some matter at least in the case of phases for matter, the phases are categorized by some very distinctive properties that are persistent, like water, right? If you heat up water a little bit, you cool it down a little bit, the water characteristic kind of doesn't change that much, right? Like that the volume doesn't change very much, but the shape of water can, depending on the container. So that's a persistent property, and the same thing for ice, and also for gas. So that's why it makes sense to kind of break water down into these three phases, at least the typical ones. It's so that we can kind of categorize them and study them in a systematic way. I don't know, Mikey, would you agree with that?
Yeah, I'd say so. I think it's the quicker way to say it. Yeah, is like you have a certain substance, right? And under different conditions, if you have a situation where this substance suddenly completely changes the way it behaves, its properties completely change, we would say that it's changed a phase. So I would say a phase describes like either like a temperature range or a distance scale over which the behavior of material is more or less governed by the same laws of physics. It's more or less the same. But then sometimes when the temperature or distance scale changes drastically, the same substance will take on a radically different behavior. And I think this is what Tim was getting at, and what we generally describe as a phase or a change in phase.
Yeah, I would say it is quite remarkable, isn't it? Though, like, given water, somehow, like water is a pretty complicated material. It's H2O, and when you just take some amount of water, depending on the temperature and pressure, generically somehow we just have three distinctive different sets of laws of physics to describe them. It's pretty remarkable, actually. For such a complicated substance, we only kind of need like roughly three sets of distinctive toolkits to describe them. And that's not it's not obvious that it can be done, but it turns out that it can be done, right?
Mhm. Right. So
So
why are there different phases of matter or anything else? Like where does this come from?
yeah, I think it comes from what we coined the universality classes, and it's just a fancy way of saying that In certain cases, in certain limits, even though you have these super complex systems and whatnot, the mathematics when you zoom out in a system kind of simplifies into distinctive categories, and these categories are the ones that are characteristic in different phases, and that's really, I think, it's the power of using phases to describe materials like water, and also universality classes can also go beyond the material that it's describing. Right? It's basically telling you that some generic set of mathematical equations always kind of emerge in a similar way. So for example, like the liquid water can be described similarly to, let's say, I don't know, the liquid of alcohol, right? As long as they're both liquids, and we don't have to reinvent the math. We can kind of we use the same, I don't know, what do you call it, the same system, the same mathematics to describe.
Same dynamics.
Yeah, basically. So basically.
Hmm.
Mm.
Interesting. So I don't know what's interesting about this. What should we say?
Well,
The fact that there are different phases in the universe.
yeah, and
Like
I
people think
guess,
that yeah. Hmm?
well, I mean, the interesting thing is we have a very similar situation for actually fundamental forces. Fundamental forces also falls into these different universality classes, at least the way we describe them in the real world. And as a result, they, maybe not as a result, but it is indicative of distinctive phases of these forces in our universe.
Okay, so it's like maybe we should just like for the audience like simplify. So we think of like three phases of matter. We think of like the same substance that can behave in three very different ways. So you get water, and at low temperatures, it's like a solid, it's like a crystal. It basically is a crystal. And then at slightly higher temperatures, it's like a liquid, completely different dynamics, completely different laws of physics used to describe how it moves. And then at very high temperatures, it's a gas. Again, completely different behavior, different laws of physics to describe how it moves. With forces, what are the different phases that forces can take on? And then uh, what is the connection between different phases of matter and different phases of forces, if any?
Yeah, I mean, okay.
So what are the three? What are the phases of forces? First off,
Yeah, I think the phases of forces we can also think of it in a similar way. Just like the phases of water usually depend on the temperature, right? You heat things up, you heat water up, you turn to gas, you cool it down, turns into water and then ice. Um, Forces can actually behave similarly, and the way to turn temperature up is you can go back in time, early enough in the beginning of the Big Bang, that temperature is higher, and you can actually see in cosmological records that these forces goes through different behavior. So temperature is definitely one aspect of it.
yeah, we don't have to talk about the beginning of the universe. Like right now, if you could somehow reach, whatever,
Right,
like
of
a
course, yeah.
billion kelvins, yeah, you would see the forces literally melt.
Yeah, and also I guess for fundamental forces, like things like temperature and pressure, they are more like external influences, right? Um, but for fundamental forces, we need to consider something that's more internal, I suppose, right?
I mean, it's still analogous to temperature and pressure, right?
Yeah, but I want to say that depending on the type of matter that exists, the phase could also change. But obviously, you can't just change the matter, in the theory. Now these are more like hypothetical kind of thought experiment changes, right? Like, I don't know if that
So what
makes
are you getting
sense.
at?
Well, basically,
What's a hypothetical?
like for example, if we add more quarks, like more types of, if we add a few more types
Oh,
of
okay.
electrons, right?
That
Perhaps
yeah,
certain phases would change, would start to change. Maybe
sure.
not.
So
Huh?
no, for sure. Yeah, 100%.
Right. Yeah. So I guess these are a
What's so
little
what?
bit different, right? Like, um, so I'm just trying to say that these are not the same thing as temperature and pressure, which we could dial up in the laboratory,
Well,
but
yeah, you're talking about dialing laws of physics, like particle number, like yeah.
yeah. So basically, like the phases of forces depending on familiar things like temperature, pressure, and also depending on the content of the theory, which you can't just dial. but it does depend on it, and then the phase could vary. So
I mean, yeah. Um, yeah, okay, I agree with all that.
as the
So what
past
else
two,
is interesting about this? Okay, so yeah, wait, you didn't tell me what the three, four phases of forces are.
yeah. So I thought about it for a long time. Um, like this is not a very good analogy. Let me just say that at first. So
Wait, why are you starting with the analogy? Why don't you just describe? Okay, so it's fair to say that like it's very generic for forces to have three different kinds of behavior. And we've been talking about forces for a while now, and we talked about the strong force and about how it has this strange behavior where, as you pull things apart, the force actually gets stronger. So that's a very weird behavior, right? We're used to thinking of forces like gravity or the electromagnetic force that are, we usually think of them as attractive, but their influence uh, gets smaller as the
mm,
distance gets farther away. But then we have this weird force called the strong force that behaves in the opposite way. As you get farther away, the strength of the force actually increases. So this is kind of an example of a force in two different phases,
mm, mm.
where the behavior is just drastically different. Um, so there's already an example of two phases, right? There's the forces like gravity, electromagnetism. When we observe them, they're in this phase where their influence goes down with distance. And we've seen an example of a force where the influence grows with distance, in the strong force.
Yeah. So technically these are so the first one, with like electromagnetism and gravity, these are called the Coulomb phase. I think that's
Yeah,
fairly. I think that's a fairly reasonable name. I think that agreed upon. And then for the strong
they could
force,
call it the Kepler phase.
is that right?
I know they could. They don't, but
Right. I think it's just in honor of Coulomb, who studied the Coulomb force. Did he discover it? I'm not sure.
1/r².
Yeah. Yeah. The force.
Yeah,
The
one over
force
r
law.
squared is Coulomb.
And that's something we're very familiar with, and the reason why we live freely in our universe is because of this long range forces. That forces get weaker as distance increases, so that my hands are not always stuck in some place. I can move them freely, roughly, and that gives rise to interesting interactions like chemistry. And the strong force has this really strange property. Not only does the force increase, but then this property leads particles that has strong force to kind of clump together. So this clumpiness is also characteristic um, of this confining. Obviously, this is a different phase. The confining phase. So far we have two. Right, there is a last one that we described last episode for the weak forces. Right.
Mhm. Wait, so like in the confining phase, the potential is linear,
Yeah, basically,
right?
yeah. In the confining phase,
Wait, what's the force then? It doesn't make sense. And the force is the
the force
derivative, so
is constant. Basically, it's like a string with a constant string, roughly speaking.
yeah, okay.
So it's not exactly like a rubber band, but it's kind of like a
Yeah.
really floppy rubber band. But the thing is, you don't see this rubber band either because of the matter content. These rubber bands are trapped, basically.
Uh-huh.
I guess the third phase that we describe is what was commonly referred to as the Higgs phase. It's basically that's a little more complex to describe, right?
Wait, what is the Higgs phase? Is the Higgs phase after the symmetry breaking, or is it like during?
I think it's after, but maybe we should clarify for the listener, right? So
Uh,
so the Higgs
well,
phase,
yeah, I'm a little bit confused by it too, so I'm gonna pick, yeah,
yeah. So
clarify.
The Higgs phase is characterized by the freezing of something, and that something is a little bit more abstract. So maybe a decent analogy is like it's like water, right? So imagine water. Usually it's freely flowing. Water molecule can go from one place to another. Um, but when the temperature gets really low, and in the universe, the temperature is basically zero, close to zero anyway. Um, the water molecule could be frozen in to turn into ice. The Higgs phase is roughly, I mean, it's not literally, but it is it's certain freedom in the theory, uh, and that got frozen. So in the electroweak theory, we have cousins of the photons and the W and the Z bosons, right? Without this Higgs mechanism, this freezing effect, the photon should be totally free to convert into its brothers back and forth, right? But then when the Higgs kind of lock that in place, freezes in, um, this becomes impossible. The photon now have to overcome some energy barrier in order to convert into other particles, and that barrier is the barrier of mass, right? So the Higgs phase is characterized by certain matter like the Higgs, locking in a certain abstract value. I guess, how do you put this? It's called the Higgs field itself has locked has frozen in and causing the freezing of particular force carriers.
Freezing temperature.
Yeah. I don't know. Is temperature the best analogy? I guess it is.
Wait, you talk about the vacuum expectation value, right?
Yeah. We're talking about the vacuum expectation. That's
Yeah,
the
yeah.
technical term
That's
for it.
yeah, that's a freezing. It's like essentially a freezing temperature, right?
Yeah. So indeed, I guess in the early universe, this freezing did happen. Like back in the
Wait, but
days.
okay. Well, what is the Higgs? Is the Higgs phase ice, or is the Higgs phase like? How come the confining phase has a very distinctive behavior? It's like linear potential, right? And then um, Coulomb phase is one over r potential. What is the Higgs phase like?
Yeah, it's
I used to know
the
this, but I forgot.
yeah it's an exponentially suppressed potential, right? It's the we call that the Yukawa generally.
Oh yeah, okay. So the power potential is the Higgs phase.
Yeah.
Oh, okay, I see. Yeah. So the Higgs phase is like, um, okay. Sorry, yeah, never mind.
But it is interesting that it seems like there are three distinct phases, but
Wait, so the Higgs phase is when the force particle is a scalar,
um
right?
mm,
Like the Yukawa pion exchange, right?
yeah, no, not strictly. Maybe we should clarify a little bit. So
How not? Isn't it? No, I think that's true.
yeah, I mean,
If you're saying Yukawa, that's a scalar mediated. So okay, to clear it up for the audience, like normally when we think of like um force particles, we think of like spin one particles, like the photon, the gluon, even the W and Z. Um, but I think it's true that in the Higgs phase, you describe the force meeting a particle as a spin zero particle, as a scalar.
no, it doesn't have to be. It doesn't have. It could be a W and Z, and it will give you that potential. It's
Um.
the spin is not a problem.
Oh yeah. Okay.
Yeah,
Well,
but I mean, you could think of these three phases as being categorized by the way the interaction behaves, right? That you have the one over r square, the famous, kind of Newtonian, like gravity or electromagnetism, and there's the linear. The force goes like, oh, I think the force is constant. The energy is proportional to distance, right? That's kind of like a stringy. It's like a floppy string. That's the confining phase. And an exponential suppression. The further you're away, it's exponentially suppressed, and that's the Yukawa potential. Um, and the force is a little more complicated than that. So those three, you can kind of distinguish it using by the forces between particles that have interactions among those fields, or those forces. But it's actually not so clear. This distinction isn't as clear as water versus ice versus
wait, Tim, is
air.
it true that the force meeting particle in the Higgs phase is always massive then?
It is, yeah.
Okay, so that's what it's the theory of a force with a massive force particle.
Yeah.
Yeah. Okay, so that's where the Yukawa suppression comes from, right? Okay.
Yeah,
Real.
I guess in other distinguishing factor is the force of these so-called force mediators, right?
So the Higgs phase is the phase of a force after it has stopped being, after it has been broken, but before it's dead.
Yeah, to some
Is
extent.
that fair to say?
I think that's fair. The force is still active, but just very suppressed, exponentially suppressed. But you can still access
Yeah.
it, right?
So the three phases are forces that get stronger as you try to pull them apart, forces that get weaker as you pull them apart. And when you have a force and that force gets broken, and then the remnants of it, like it's like the remnants of a soon to be dead force.
Yeah. But actually,
Wow, that's interesting.
should we go through this the similarity actually between the confining phase and the Higgs phase? Is actually a very
Um,
interesting topic.
yeah, no, I think we should wait, but hold on. That's because I never thought about it that way. Just like if we just think about forces, and those are pretty much the only kinds of forces you can imagine, right? Like if you
Um,
consider all the different types of potentials, like linear, log, inverse, right? You can actually categorize the behavior of all the different forces,
yeah,
right?
I hesitate to say yes because I think technically there could be other phases. I don't want the audience to
Yeah, but
think
like
that.
in a wacko universe only, right? Like in a reasonable universe,
Yeah,
this is what you'd expect.
I think it's fair to say that these three phases that we refer to, the Coulomb,
Yeah,
the confining, and the Higgs phase, they are the most generic. Like we would expect,
yeah,
like any typical universe, I would expect a combination of a few of those.
yeah.
Just because. Now there are some more exotic phases, just like phases of
No, in
matter,
fact, you
right?
could say that the architecture of the universe is nothing but an exquisite selection of those ingredients.
Right. Yeah. 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 Although there are crazier ones, only in the theoretical land that people have come up with really exotic models with just the Goldilocks amount of matter and forces conditions to have really exquisite, like, you know, unique phases. But those are probably unlikely to happen in our universe, I would imagine.
Yeah. Um, man.
Should we go?
So,
Should we go over the similarity between confining phase and the Higgs phase? I mean, that's actually
yeah,
a super
yeah.
interesting
Wait,
topic.
combining phase, yeah, okay.
Yeah, because on the surface, I mean, it's super interesting, and it's not obvious at all, right? On the surface, they seem to be very different phases, right? Because on the one hand, you know, you have energy that increases as the distance between two particles increases, right? On the other hand, you have an exponential suppression. So what gives? And this comes back to um, you have to zoom out a little bit, basically, right? Because in the
Wait, should we talk about how it happens in our universe with the quarks
yeah, yeah,
and
yeah,
how it happens?
yeah, yeah. I think so. I think so. So how does that work? So if you zoom in really close, obviously, then yeah, these forces will increase
Right.
as distance increases. But if you just zoom out a little bit, right? Because the confining force is so strong, um, when you have things like quarks and gluons, they're pretty much stuck in one place. You don't see them. You don't see individual ones. So if you zoom out just a tad, you, instead of seeing quarks and gluons, you actually see these composite particles like protons, neutrons, and also mesons. I think the mesons are maybe the audience might not be as familiar, right?
Yeah.
These are
But
yeah.
yeah, the simplest. It's just a quark and an anti-quark thrown
Right.
together.
It's like a dumbbell basically, right?
Yeah.
It's so if you zoom out a little bit, it turns out that the forces between these particles, not the quarks and gluons, between protons and neutrons and mesons and whatnot, actually has the same behavior as the Higgs phase. It's actually an exponentially suppressed Yukawa potential, right? And that's very interesting, isn't it? I mean, on the one hand, you can blame, maybe mathematically, we can blame just universality classes. It's like, oh, there are only so many equations to govern fundamental physics, so inevitably, uh, but just by chance you get something
No, I don't
similar.
think so. It's in line with what we said before that the Higgs phase happens when you break a force and it's the remnants of it, right? And one way you can break a force, as in when I say break, I mean remove its existence from the universe, is by confining it away. Um, so when you have a force and then you kill it, smush it, hide it, whatever. Um, One way to do that is by having it confined. Then when you zoom out, you can't really see it anymore, but there's something left over. It's these composite particles that now act as the mediators for this exponentially suppressed force.
Right.
So I think it happens in a universe in a very kind of generic way, though, right?
Yeah, I mean it is generic. Well, I was just playing the devil's advocate a little bit, right? Like there's no reason to think that they are related. It might just be, you can argue that, hey, that seems like an accident, but
Yeah,
that turns out to be not the case. What's
yeah.
interesting is that it turns out that there is a mathematical relationship relating the two, actually, and that's
Mhm.
one of the deep insights in theoretical physics. That
Yeah.
these are perhaps it's not just by accident that these potentials are somewhat similar. There is actually a mathematical language to perhaps translate.
Whenever you see one, you will see the other. It's guaranteed. It's it would be ridiculous for that not to be true, right?
Yeah, and I guess there are toy models where theoretical models where you can literally convert from one phase to another like smoothly and see that these the two similar properties emerges, right? um but so anyway
Yeah.
and
So,
any additional thoughts about the phases of forces?
um, yeah, I think yeah. So there's this relationship between phases of force and phases of matter. God, I wish I had spent a little bit more time thinking about this. I'm sure I'd have a stronger opinion about it. But um, do they? I mean, in a sense, you can think of them as very similar, right? Like if you think about like the van der Waals force of like between like air molecules, and then like that's a very different force behavior. So you can think of phases of matter as being due to a change in how the intermolecular forces are behaving. And yeah, you can actually take that analogy somewhat interestingly far in some situations. So I think yeah. Before this, I was skeptical, but I think there's a pretty good analogy there, and I think you can think of this what we described in terms of the phases of forces as an underlying explanation for why this phenomenon exists in our universe, that things can change phases and suddenly drastically change their behavior. It's Yeah, it's interesting and one of the fundamental ingredients to our universe, I would say.
Yeah, I guess I would add that the phases of forces highlight one interesting fact is that the if you have the same mathematics or more or less 99% same mathematics, just by the virtue of slightly different mixtures of composition of matter and temperature and other properties, you can actually get these completely almost different behaviors, right? Like if you have, before these complicated mathematics, if you see a force that's in the Coulomb phase versus in the Higgs phase, on the surface you would say they have nothing in common. Like why would we expect one theory to be able to describe them all? That's not obvious at all. But what's interesting is that by thinking about it using fundamental physics and by exploring these phases, we now know that one mathematical model, these the theory of quantum field theory, is able to come up with to give us all these diverse behaviors, and I think that's really marvelous. That's not obvious at all, right? And that's kind of the power of our approach to particle physics, I would say.
So, all right.
All right, I
How
think
are we supposed to close this?
we're
I forgot how to close this.
well, I think we're at time, and well, I guess we would like to thank our listener for tuning in, and we'll see
Uh-huh.
you all next time.
Good night.
All right. Bye.
Bye bye.
Okay, let me stop streaming.